तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
We had started discussing about negative feedback structures in op-amp. First, we gave full output feedback, negative feedback, and then we got V naught equal to Vi. V naught equal to A by 1 plus A being very large, V naught is very nearly V naught over Vi. This is V naught over Vi, very nearly equal to 1. Buffer, it is called unity gain amplifier. Another one where we sampled V naught, this was V naught into R1 by R1 plus R2, where beta was R1 by R1 plus R2. Definition that. So, beta times V naught was fed back. Therefore, ultimately according to us, Vi should be equal to beta times V naught. This voltage should be 0 if it is working at finite output situation. So, we saw that according to equation A Vi, 1 plus A beta was V naught. Okay. This was very nearly equal to 1 over beta, and this was equal to 1 plus R2 over R1. Therefore, we can design a non-inverting amplifier of gain 1 plus R2 over R1, which is 1 over beta. So, this is done by applying H feedback. So, now we will go into the 2-port parameter technique that we have used. Now, we will introduce all the non-idealities associated with the op-amp. First, we said op-amp is a structure with forward transfer parameter very high. Okay. So, A was tending towards infinity. In the G matrix of this, right, the other 3 parameters were 0. But now, the other 3 parameters are not 0, they are finite. That means finite input impedance, finite output impedance, and finite non-infinite gain. So, when we consider such an op-amp, that means such an op-amp equivalent we can get for any configuration of cascaded amplifiers. This we know how to obtain. Once you obtain this and then give a H feedback using a passive network R1 and R2, this R1 R2 passive network samples the output, feeds back, okay, beta times V naught, or R1 by R1 plus R2 times V naught, okay, at this point as the feedback voltage. Now, under that situation, what happens in an actual situation? So, we would like to apply now H parameter for a voltage controlled voltage source analysis with H feedback. We would like to use H parameter. So, composite H parameter will write. So, Hi and Hf we get by short circuiting the output. So, we short circuit the output. Then you can see that the feedback comes out of it, and the feedback is in series at the input. You can see this is the amplifier input, this is the feedback network. Okay. So, these two are coming in series with the actual input. So, it is shunt at the output and series at the input. So, the H parameter of the composite network is nothing but Ri, the input current flows through Ri, and parallel combination of R1 and R2 because R2 is grounded. So, Ri plus R1 parallel R2. That is HI. Once again, HI is nothing but the input impedance of the composite structure, which is Ri of that amplifier, and then R1 parallel R2 that of the feedback network. These things simply add. So it is very simple to evaluate this. Next, let us evaluate the HF, which is the short circuit current gain. When the output is shorted, what is the current gain? So the current output I naught divided by II. II is the input current. So I naught by II is what is defined now under the situation of output being shorted. So if II is the input current, okay, this II will flow through Ri and develop a voltage Vi1 minus Vi2 as II into Ri. So this voltage is II into Ri because the current II is flowing through it. That means this is II into Ri. Vi1 minus Vi2 is II into Ri. Next, if this is the voltage, what will be the current through the short circuit? Ri divided by R naught, but flowing in the opposite direction that we have assumed. So negative sign indicating that it is actually flowing this way. So A times Ri divided by R naught. This into II, okay, divided by II is the current gain. That is the output current. This is not the only current. I naught has this current as well as you can see this input current comes like this, and portion of the input current, what portion? R1 by R1 plus R2 of the input current is also going out. That means minus R1 by R1 plus R2, okay, divided by II. So that is the current gain. Once again, let us see, going through the amplifier, this voltage is II into Ri, and therefore A times II into Ri is the voltage here, and that will drive a current A times II into Ri by R naught in the opposite direction, so minus. So A into Ri into II divided by R naught divided by II. So here II also has a part of current going in the forward path here. II into R1 by R1 plus R2 is flowing this way. So these two are the parameters HI and HF. Next we have to evaluate open circuit input. Input is open. Okay. Input is open. Okay. So this source is removed. So what happens? There is no current in this. That means this is inactive. So there is Vi1 minus Vi2 equal to 0. So this is not. So R naught is shunting this. Okay. Apart from that, R2 plus R1 is shunting there. So this H naught is 1 over, okay, R naught plus 1 over R1 plus R2. This is that of the amplifier output conductance. This is the feedback network output conductance. As far as feedback voltage is concerned, if I apply V naught here, the only voltage that applies here comes here is R1 by R1 plus R2 times V naught. So R1 by R1 plus R2 times V naught. That is HR. That is positive. So we have simply written, okay, the composite H parameter of this fairly complex feedback network where nothing is neglected. Now, if you include the source impedance here, this is the situation. Source impedance is coming in series with Ri, okay, and the load impedance in the case of H parameter always comes in shunt with the output impedance. So, this is the total situation where we are now considering also load impedances and source impedances. So, this is giving you the complete picture of a negative feedback situation with operational amplifier. Nothing is neglected. Now, of course, there is no point in keeping things which can be neglected. Now, I would like you to come out with some definitions, practical definitions. See, what did we say about the forward transfer parameter here of this is A, which should have been infinity, Ri which should have been infinity, 1 over R naught which should have been infinity. So, if actually A is infinity itself, that is sufficient to make this infinity. But we can see that the other parameters will make this a very huge value. Okay. So, having R naught equal to 0 and Ri equal to infinity and A equal to infinity means this is really speaking infinity cubed kind of thing, that is a high value, a third order high value here. Okay. So, this therefore is very huge in a practical op amp itself, wherein A is anyway high, Ri is going to be also high, R naught is going to be very low. So, there is no point in retaining this, which is always a fraction, right. So, this can be ignored compared to this always. That means the forward transfer parameter contribution due to passive device can be ignored. Here the active device has not contributed to any reverse transmission at all, that is something that you have to remember. Only the passive device has contributed to the reverse transmission. So, now you can find out the loop gain. This is an important thing. This should be much greater than 1 and this should be negative for negative feedback, that you can verify. This is negative and this is positive. So, the loop gain is negative, is A into Ri by R naught into, let us call this beta, because we have defined this R1 by R1 plus R2 as beta. So, A Ri R naught into beta divided by, now you can consider this into this Ri. Now, Ri is normally very huge compared to beta R2 plus Rs. Rs is anyway going to be source resistance. Normally, Ri is going to be very high compared to beta R2 and Rs. But then we cannot Ri plus Rs to beta R2. Here normally R naught is very low compared to R1 plus R2 and RL. Okay. So, normally this factor alone becomes significant. So, here this factor alone becomes significant. So, that is the actual loop gain. Okay. Before we rub it off. So, you can see here A, one thing that is supposed to be high, Ri which is very high, R naught very low. That means this is infinity to the power 3. Here Ri which is high, R naught which is low. This is infinity squared. So, loop gain is still very high. Okay. So, generally this loop gain is going to remain very high, and this Ri by R naught will get cancelled with this Ri by R naught, and it is really A into beta, which we had earlier defined as the loop gain there, A into beta. So, you can see here, I will therefore take this Ri and take this R naught, retain the actual loop gain as minus A beta. And how is it different from that? Divide Ri by Ri here, and here okay, multiply by R naught. So, you can see that it is the normal loop gain minus A beta, okay. Under the situation Ri is infinity and R naught 0, you can put Ri equal to infinity here, this will go to 0, R naught 0, this will go. So, it is minus A beta. Under the situation Ri is equal to infinity and R naught equal to 0, the loop gain is equal to minus A beta for Ri equal to 0, R naught equal to Ri equal to infinity and R naught equal to 0. Otherwise, it is going to be dependent upon this Rs by Ri ratio in relation to 1. Similarly, R naught by R1 plus R2 ratio in relation to 1. So, now what is the input impedance? What is the forward transfer parameter? Okay. All these things we can now determine. First, let us find out the input impedance. You see, input impedance is going to increase over and above what? The original input impedance. Okay. The original input impedance is Ri plus beta R2 plus Rs. Okay. And the present input impedance will be 1 plus loop gain times the original impedance. This can be also found out by taking the matrix delta H as this into this plus this into this, okay. Find out delta H and divide this by delta H, that is the input conductance, right. Instead, I have also told you that original input impedance gets modified by a factor of 1 plus loop gain. So, this is the original input impedance Ri plus beta R2 plus Rs. So, that is getting multiplied by 1 plus loop gain. Okay. So, actual loop input impedance Rin is Ri plus Rs plus beta R2 into 1 plus A beta divided by that factor. That is actually the input impedance. So, you can see that it is increasing very much. Input impedance seen from this side, which is going to include Rs, right. So, if you remove Rs, it will be input impedance without Rs, right. From this you subtract Rs, okay, that is the actual input impedance seen from here. Okay. So, Rin of the amplifier really speaking is this. Okay. So, this is including Rs. Now, output impedance. Once again, you can do it by this method. This one to be divided by delta H, the matrix of this, that is the output impedance, or original output impedance is this, right, that is output conductance is this, right. So, that has to be reduced by a factor of this, right. So, the conductance is increased by a factor of 1 plus loop gain. So, original output impedance, okay, 1 over R out is going to be this this is the original output conductance into the same factor in which you have to remove the effect of 1 over RL, this 1 over RL that is coming here. So that actual output impedance, so this is including shunting effect of RL. So you subtract from this 1 over RL, then you will get the actual output impedance. So you see this conductance increases enormously, that means output impedance is brought down considerably. Now finally the gain, this divided by the loop gain. So as far as this is concerned, this divided by delta H. Delta H you will see is nothing but this into this, that is going to cause only infinity square, but this into this is going to get added to it. So delta H has major part of it as A Ri by R naught into beta. This is infinite cubed, this plus this factor, right. Into 1 over R naught plus 1 over R1 plus R2 plus 1 over R. This is actually this is with plus, right. So this is the forward transfer parameter, out of which this factor is much less than this. So this can be ignored. So what do you see? It is simply becoming 1 over beta. So this factor really gets cancelled here. So this becomes 1. This is nothing but V naught over Vs. Please remember, this is nothing but V naught over Vs. This is the loop gain, V naught over Vs. So finally we can say that as far as the gain is concerned, it is very nearly equal to 1 over beta, and input impedance is equal to this, output impedance is given by this. So these are the exact values of the actually G matrix. One is Gi, that is really Gi, this is G naught, this is Gf. So these actually give a fairly good idea as to how to select the value of R1 and R2 so that this approximation becomes valid. You can see that if Ri is known to you, then you can select this Rs and beta R2 such that this is predominantly determined by Ri. Here also you can, if R0 is known to you, right, R1 plus R2 and RL can be so selected that this becomes negligible compared to 1 over R0, right. So basically Ri gets multiplied by 1 plus A beta, R0 gets divided by 1 plus A beta, and A gets divided by 1 plus A beta. If Ri and R0 were to be made respectively infinity and 0. So this concludes the discussion about H feedback. The next circuit that we have discussed as far as this is concerned is the Y feedback, which is the only other negative feedback possible with operational voltage amplifiers. Now, let us consider Y feedback as applied to the operational amplifier, negative feedback. So, we have this op amp. The feedback is from the output, shunt at the output. That means output voltage is common to both amplifier as well as the feedback network. Shunt at the input, again the input is voltage is common to both the amplifier as well as the feedback network. So, the feedback network is RF, a single resistor connected from output to input. Output it is coming in shunt, input it is coming in shunt. So, this is shunt feedback or called Y feedback. Now, a simple way of analyzing this is, as I told you, if A were to be infinity, if A is infinity, we know that this is grounded and this is a nuller. We have introduced this equivalent earlier also. So, this voltage is 0. Why? Because if this is finite, V naught by A is this voltage, A is infinity. So, this voltage is pulled down to 0. This therefore is called virtual ground. This is an important concept. If I ground the amplifier and if the amplifier gain is made infinity and if the output is finite and output is connected to input through negative feedback, then it is always this potential that becomes virtual ground. Potential here is the same as that of the ground potential, virtual, which means the current in this is Vs divided by Rs, and this current cannot go into another, so it can only go into Rf and develop a potential which is Vs by Rs into Rf, with this end positive and that end negative. So, this is at ground potential and therefore, output potential V naught is nothing but the potential across Rf, because this is at ground potential, virtual ground. So, this is minus, because this is plus and that is minus, Vs into Rf divided by Rs, independent of RL, right? Because this is virtual ground, the current pumped into this is Vs by Rs, and the same current is forced to go into this feedback network Rf, develops a potential Vs by Rs into Rf, and therefore, V naught is, this is therefore called an inverting amplifier. Why inverting? There is a phase shift of 180 degree here. If the input amplitude is increasing, here it will be decreasing. So, there is a phase inversion, inverting amplifier, and the gain is Rf by Rs. So, basic concept here that is to be highlighted is that this point is always at virtual ground. That means, this is a current summation point. Any number of currents can be added here, and all those currents will be pumped into the feedback network. So, this concept is very useful in a variety of applications of converting current into voltage. We will see this later. But now, suppose this is not infinity, then what happens to this? We therefore will modify this. If this is not infinity, this potential is minus V naught divided by A. It is not 0, because this is V naught. So, this is minus A. So, this potential is minus V naught by A, and therefore, this current is not Vs by Rs, but it is Vs minus V naught by A, that is Vs plus V naught by A by Rs, and it is this current that will be going into the Rf. Therefore, the potential is going to be Vs plus V naught by A divided by Rs into Rf instead of the earlier Vs into Rf by Rs. Therefore, V naught is going to be not 0, because this potential is not 0. So, it is minus V naught is going to be minus V naught by A, this potential, okay, minus Vs plus V naught by A into Rf by Rs. So, if A is infinity, you can just look at it. This will go to 0, this will go to 0, and we will get back, okay, what we had earlier, that is minus Vs into Rf by Rs. Therefore, V naught into 1 plus, we have 1 over A, okay, plus, okay, Rf by Rs over A from this, and this is equal to, okay, this factor, these two factors have been taken into account, and minus Vs into Rf by Rs. So, V naught by Vs, which is the transfer function, now becomes modified at minus Vs into Rf by Rs divided by 1 plus Rf by Rs by A. So, you can see, if A were to tend to infinity, this is what it was. With A finite, we have that getting modified by, again, this is the loop gain, 1 plus loop gain. This is the loop gain. If you look at this, A into Rs divided by Rf is the loop. You short circuit this, A into Rs by Rs plus Rf is the loop gain here, right, if you break the loop here. So, that is what it is, A into 1 plus 1 over loop gain. So, I will write this. So, if the loop gain is very high compared to 1, this goes towards 0. So, 1 plus 1 over loop gain. Right. So, let us now investigate this using proper parameters. What I mean is, just as we did in the case of H parameter, okay, we will investigate the feedback with Ri, R naught, etc. also taken into account. So, instead of making this approximation, we will retain this just like this. Now, we will consider the same circuit without neglecting Ri and R naught. So, that means here, instead of it being an open circuit, we have Ri, same thing, and here the output R naught, and okay, if this is let us say Vi here, okay, this is Vi, A times Vi there. If this is positive and this is negative, this is A times Vi. So, this is the equivalent circuit now of the op amp. Then how does it work? So, once again, now we will consider Y feedback. This is Y feedback. So, composite Y parameter must be determined. What is composite Y parameter? I short circuit the input and find out Yi and Yf, short circuit the output, Okay, short circuit the output, find out yi and yf, short circuit the input, find out yr and yo. So let us do that. So short circuit the output. So we have here 1 over Ri, okay, when I short the output, one over Ri comes in shunt with 1 over Rf. 1 over Ri comes in shunt with 1 over Rf. This is that of the amplifier, this is that of the feedback network. As far as the forward transfer parameter is concerned, if the voltage is Vi here, okay, this way, right, A times Vi is the voltage there, and the current is AVI by R0 that way, right. But actual input is positive here and negative here. So let us put it that way. Please understand, if this is Vi, then I should put here minus and plus, indicating that there is an inversion, right. So if this is Vi, okay, there is an inversion, okay, A times Vi here, this is applied to the inverting terminal. So the current is going to be pumped in, right. If this is plus and minus, it will be pumped out. So now pumped in. That means for an input current like this, this will be having a current this way. So A times, okay, Vi by R0, okay, is the output current, okay, output current divided by input voltage, this parameter. So A times Vi by R0 divided by Vi. So A by R0 is the YF of the amplifier alone. What about the feedback network? If I apply Vi here, the current Vi by Rf will be going out. So minus 1 over Rf. So you can see A by R0 is due to amplifier, minus 1 over Rf is due to the feedback network. Simple. Next, I short circuit the input and apply voltage at the output. The feedback parameter YF, right? When I apply voltage V0, if I short this, V0 by RF will be going out. So minus 1 over RF is YR. For the amplifier, there is no feedback. Okay? So only the passive network has feedback. As far as output conductance is concerned, this is 0, Vi is 0. Okay? So this is 0. So 1 over R0 plus 1 over RF. These are the short circuit parameters, very simply obtained by definition. Then, as far as the input is concerned, the source admittance is added in shunt, 1 over Rs. As far as the output is concerned, you can add 1 over RL, so that effectively you have strictly speaking, the source that you have to use here should be compatible to that of the Y parameter. That means instead of Thevenin source, you use Norton source, right? Which means you put a shunt resistance of Rs and a current source of Is, right? Instead of using Thevenin source. Right? Now, this is the composite Y parameter of this fairly complex Y feedback network. You can now find out the loop gain. Once again, you can see because A is coming here, okay, R0 is coming here, so this is infinity squared, right. So this can be neglected, right. and loop gain is 8 by R naught into minus 1 over RF divided by 1 over Ri 1 over Rf plus 1 over Rs into 1 over R naught 1 over Rf 1 over Rl. This is the loop gain, right. So, we can again make the approximation R naught can be taken inside. So, 1 R naught R naught. So, I will rewrite it 1 plus R naught by Rf plus R naught by Rl. Once again Rf can be taken inside this. So, one plus Rf by Ri Rf by Rs. So, I can see basically the loop gain is minus A. Basically the loop gain is minus A, right. Or if you were to really make R not equal to 0 and Ri equal to infinity, then the loop gain is minus A into 1 plus minus A into Rs by Rs plus Rf. That is what we have got. This will go to 0, this will go to 0, this will go to 0. So, it will become minus A into Rs by Rs plus Rf. But strictly speaking, right, Rs should be made equal to infinity also, because it should be driven ideally by a current source. It is a current control thing. So, Rs also, if it is made equal to infinity, then actual loop gain is minus A, right, if it is strictly a current feedback. So, you can see that this is the loop gain, and everything decreases by loop gain, 1 plus loop gain. That means Ri becomes Ri divided by this factor. The original input impedance, input conductance is this. This conductance is going to be multiplied by 1 plus loop gain. This conductance is 1 over R naught plus 1 over Rf plus 1 over Rl. So, this again decreases, output impedance decreases, or output conductance increases by 1 plus loop gain. So, we will see how this gets now modified. As far as this parameter is concerned, it will become minus A divided by R naught. This is the Y feedback. So, we have to convert it into Z parameter. So, what is the Z parameter? Minus A by R naught divided by this into this plus this into this. In this, A by R naught into 1 over Rf is dominant factor, plus you have that factor, which is 1 over Ri plus 1 over Rf plus 1 over Rs into 1 over R naught plus 1 over Rf plus 1 over Rl. This factor is negligible compared to this, because you have A going towards very high value, 1 over R naught going very high. Strictly speaking, therefore, this will converge towards minus 1 over Rf. That is 1 by minus 1 over Rf, or this is going to be equal to minus Rf. Here, A by R naught will get cancelled with A by R naught. So, this will be 1 by minus 1 by 1 over Rf, or minus RF. So, the Z parameter ZF is going to be minus RF. Okay. Now, all these parameters Zi is going towards 0, Z naught is going towards 0 by a factor which is 1 plus loop gain, okay, from the original value. So, please see this, right. This becomes insensitive to operational amplifier gain. It is simply, okay, the impedance connected between output and input. So, if I apply IS here, what it means is this IS will almost totally go across this. This is virtual ground, and the output will be minus IS into RF. Okay. So, now we have seen Y feedback and H feedback as applied to the operational amplifier. As I told you, these are the two negative feedback structures available to us. I would like to at this juncture also discuss what happens if we give positive feedback. So, I want to know, in the light of the op amp being made available to us, we have understood negative feedback, and we have seen that negative feedback improves the performance of the amplifier enormously, brings about linearity, brings about insensitivity, okay, and also reduces effect of noise, etc. Now, let us see what happens if we give positive feedback. So far, we have been concentrating on negative feedback and its virtues. Let us now consider what is positive feedback. Whether it is going to be useful at all is one point we would like to see, and how far positive feedback can be given. This is the negative feedback circuit illustrating voltage negative feedback. Output voltage is sensed, okay, beta times V naught is fed back to the input, which is the inverting input. This is plus. So, Vi, okay, Vi is the actual input minus beta V naught. Vi minus, this is important, beta V naught is what the amplifier takes as the difference signal, right. Vi, that means output voltage is fed back, okay. V naught is going to be in phase with Vi, okay, because it is applied to plus. So, beta V naught is in phase with Vi. If beta V naught is in phase with Vi, Vi beta V naught, they are both in phase voltages. So, Vi minus beta V naught means this beta V naught is opposing the original input, opposing. The feedback voltage is opposing the input, and that is the resultant voltage that is applied to the amplifier. So, Vi minus beta V naught, that times A is equal to V naught, and from this we have got V naught over Vi as A by 1 plus A beta. This we had discussed earlier. Now, I am going to make it different. This is going to be minus and this is going to be plus. So, V naught and Vi are out of phase, right, and this beta V naught is going to be coming in series with Vi. Okay. So, what happens here now? Earlier Vi minus beta V naught was getting multiplied by A, but now Vi minus beta V naught is getting multiplied by minus A. That is the thing. Wherever A was there, put minus A and you will get the equation, because earlier Vi minus beta V naught was multiplied by A. So, now Vi minus beta V naught is going to be multiplied by minus A because of the inversion. So, this becomes minus and this becomes minus. So, this is what happens with positive feedback. This is called positive feedback. Okay. You consider ground this is A, this is beta times V naught. That means, if I have Vi here, A times beta times Vi will appear here. The loop gain is positive. Okay. If this is Vi, this will be A times Vi and A times beta. Okay. So, loop gain is positive now. Okay. So, you get minus A by 1 minus A beta as the gain. So, if A beta is less than 1, let us say beta is 0, no feedback situation, V naught over Vi is going to be minus A. If beta is finite, but A beta is less than 1, then the gain is going to be greater than A, because A is 10, let us say. A beta is 0.9. This is 10 divided by 1 minus 0.9, which is 100. Right? So, from an amplifier of gain 10, I can get an amplifier of 100. So, using positive feedback, you can increase the gain. Right? This is an advantage, but then it is very sensitive to that. If A beta becomes 0.99, okay, it will go to 1000. Right? If it is 0.999, it will go to 10,000. Right? So, a small variation in A beta will boost up this gain enormously. If A beta becomes equal to 1, this goes to infinity. A practical way of obtaining infinite gain amplifier, okay, is this. Now, question is, what happens if A beta becomes greater than 1? We will discuss this in the next class. That is called regenerative positive feedback. Until A beta equal to 1 is less than 1, this can be still used as an amplifier. Beyond A beta equal to 1, beyond A beta greater than or equal to 1, this is not possible to be used as an amplifier. Okay? That is called regenerative positive feedback, which is finding also application in a large number of circuits. We will discuss this later. The positive feedback with A beta between 0 and 1 is also used in what are called comparators. Right? Discuss this in the next class. So, positive feedback after all may be quite useful in certain other applications other than amplifiers.